Hi, this is a video to show how to do a two-way ANOVA in SPSS. We have two factors, sex with two levels, male and female, and the second factor is parental educational background with three levels, high, medium, low, and a dependent variable for math test. So we want to see, does the level of math test, does it depend on the gender of the student and on the background of the parents, the education level of the parents. So we're going to analyze, we choose the general linear model, and to univariate, we just use one variable, and I had clicked these over already. So we choose math as a dependent variable, and then gender students as a fixed factor, a highest education as a fixed factor. Then we go into plots, where we choose gender on the horizontal axis and parental background as separate lines. We add that, and then we take the parental background on the horizontal axis and the gender on the separate lines. It helps to have these graphs, these plots, two plots, and that way, if you flip the axes around, you get a better impression of what's going on. It makes it easier to detect interactions. When we have lines crossing, it is an indicator that there might be an interaction. We then have to test that significance with a statistic method, right? We see there might be something, but we want to see, is it statistically significant? Then we want the post hoc test for the gender and the background. And we also want the descriptives for the factors and the interaction. You see, SPSS automatically added the third component, the interaction by itself, because it knows we're doing a two-way ANOVA. So that we have other possibilities to choose, but here we're keeping it straightforward, and we go OK. So you see, just by the syntax, there's a lot more going on. First, we get this warning because it tells us, hey, for gender you only have two levels, so I won't do a post hoc because it doesn't make sense to do I can't even do multiple comparisons. You know if it's significant or not already by looking at the main effect. Here we see between subject factor, just an overview how many people are in each group. So 51 girls, 49 boys, and then the three educational levels. We see more than half are from a lower educational background, about a third have an undergraduate degree, and a little bit more than 10% have a doctorate or engineering degrees or whatnot, whatever counts as higher education. Then we have the descriptive statistics. We see this box is the girls with parents from a lower educational background, girls with parents with an undergraduate degree, and girls with parents of a higher university degree. These three, same thing for the boys, and then the overall total for each of the educational groups and the overall total for the entire population. The total for the genders is the last line here. This is the total for all boys, for all girls. This is the total for all boys. Then here we have the test for homogeneity of variance, right? Are those variances the same all over the groups? We see we barely keep the null hypothesis, right? If it was below 0.05, we would say, okay, we have some differences in the variances here in the groups. If that were the case, we might want to look at it in more detail, and you'll have to think about if we really can do an ANOVA or not. This, in the one-way ANOVA, this was the ANOVA table. This is where we know if we find differences between the groups or not. We ignore the first two lines, and we come down here to the first main effect. That's gender, sex. And we scoot over, we see the mean squares for gender is 75, and we know that the within variance, which is now called error, it used to be called within, but it's the same principle. We divide the mean squares in the group between the groups of gender divided by the within groups mean squares. 75 divided by 36 is about 2. And then we test, hey, is this 2? What's the chance of getting a 2 if there really was no difference in the population? And we see we are not statistically significant, so we keep the null. We fail to reject the null. There's no difference between boys and girls. Then we move on to the next main effect, which is the parental background. We see here between those groups there's a mean score of 290, which when we divide that by the 36, it's an F value of 8, which is really high, right? There's 8 times more differences between the groups of education than within those groups. So that's highly significant. If there was no significant, right, here we see it, although there's about double, it's still not significant. As long as there's not significantly more variation between the groups than within the groups, we do not speak of a significant effect. And then the third component that we look at is the interaction between factor A and factor B. So we have factor A, factor B, interaction factor A, factor B. And here we look as well, 36 divided by 63 divided by 36. The F value is a little bit below 2. That is also not statistically significant. So we conclude we have no interaction effect. So it doesn't matter if you're a boy or a girl, and the background, the influence of the background does not matter depending if you're a boy or a girl. We could have imagined that, for example, boys do okay in lower educational backgrounds, whereas girls suffer more from being in a family that has less education. But this is not the case. Then we see the marginal means, which is basically the estimate based on our data, but that's the estimate for how would it really look in the population. So that's why these are a little bit different than the actual values up here. Again, that's a little bit like what we did for calculating the variance of the population, the standard deviation of the population. We divided the variance by n minus 1 and not just by n. So then we move down here to post hoc tests. We do the pairwise comparisons, again with the Sheffey test, and we see is there a difference between no education and undergraduate. -3, we know, okay, no education is 3 points lower on the test than undergraduate. And this is, statistically speaking, not significant, because this is still lower than still higher than 0.05. Same thing for no education and university. We look at what is the difference. It's -6.9. So here also the no education have lower test scores than the university kids. But then they are, but here it is statistically significant. So just from this box we can conclude that children with a background, lower educational background, have lower levels than the children from the university. But there's no difference from the lowest educational category to the middle category, to the undergraduates. Then we move on. Undergraduate no education, we just did that. It's just the sign changes. So the difference is the same, and also the significance of this difference is the same. And then we move on to undergraduate university. This is new. Is there a difference between these two? We see the difference in points in the test is -3.8. So the university, the undergrad do score lower than university, but the difference is not statistically significant because 0.117 is higher than 0.05. We do retain the no. This box here is also interesting because it tells you which groups are the same, how do groups differ from each other. So for example, there's one subset that goes together and the other one goes together. So this tells you no education is not different from undergraduate, right? They're not different from each other, and university is not different from undergraduate. Those guys go to each other. This is another way of telling you that, yeah, the university and no education are different, because they don't appear in the same group together. Now we move on to our plots. These are fantastic to get an overall impression. You could actually look at the graphs right away. So you see here the girl are in the no education are the lowest, then the undergraduate are in the middle, and the difference to the university is smallest. And if we go over to the boys, we see actually the no education are not quite as low. They're almost the same as the undergraduates. And then we see the university is way up here. way higher. So we do have some fanning out, some fanning in going on between the lines. Could maybe be a little bit of something of interaction. And then when we look at this, we would think, oh boy, yes, those lines cross. There could be an interaction going on. Then, however, we do the statistical test to see if this is really a significant interaction or not. Right? So we see that it flip-flops. Girls are the boys are the green line. Boys are higher than the girls. Then they're lower, and then they're higher again. So every time you see that these flip-flops, that's an indicator of interactions. And if we did find interactions, we would actually go look at the differences between the individual scores. And I'll post in another video how you would do that exactly. How could we test each of these scores with each other? That's what the interaction would mean, right? In class, we went right away and we said, okay, the interaction, if there's any, it's got to be coming from here. So we went ahead and just compared these two means with the t-test. But there is more sophisticated way to do it. In class, I created a variable which was just one variable that collapsed all the two groups into one. So then we had 6 different groups. Right? We had all the 6 different groups. Right here, 1, 2, 3, 4, 5, 6. Compare all these together, and then you could just run an ANOVA because you only have one factor left. And then in that ANOVA, you can ask for the post hoc comparison. You can ask for the Sheffield test, and then it will run these comparisons. And there you can see which groups actually differ from each other. Where is the significant interaction coming from? Okay, this was the two-way ANOVA, and that was it.